of Riemann sums and fundamental theorem of calculus. You look at the problem in terms of Riemann sums, the second one, that we're about to do the third one, and actually calculate that Riemann sum and using fundamental theorem of calculus. All right? So that was this area between curves. Today I introduce average values. So here's one example. Suppose this electronic lottery machine that generates number using this formula. The machine was generated by this formula. If you turn it on, and after you turn it on, at some point if you hit the button, and if that was 5 seconds after the machine was turned on, and this generates 110 plus 51 times the sine of 5 times 500 radian plus 49 cosine 77 times 5 radian. Whatever the number is, it spits out the number. Next person, some interval of time, hits the button, it's going to generate a different number, and so on. So if there are many contestants, or some contestants keep doing this one, and we're getting many numbers. Suppose we tried like 300 times. So this spit out 300 different numbers. All right, because the sine function, it doesn't go to infinity or anything. It's pretty small range. So if you have 300 values, what is the average value out of this random looking numbers, right? And you're going to add all those 300 numbers and divide it by 300, right? That's how you calculate the average. So that's the question. If you keep doing that, maybe 3,000 times and so on, what could be the average value we get out of this? That is right. It is very close to the area under curve. So here I sketched the graph of that function. This is time interval between 0 and 1. As you can see, it fluctuates really quickly, so that, with the human senses, it's very difficult to detect. To get if I want 150, I should hit that button at some point. It's very difficult to decide that. So if you hit randomly hitting the button, we expect that you will going to get number in between 0 and little over 200, some random number popping out, right? So that's the graph of that function. And I think its randomness kind of makes sense. Unpredictability is described using that, explained in that graph. Here's a slightly simpler setting. So here's average value. Let me go ahead and grab everything. So I include the title. It's third application, average value. Suppose we have a function just like the ugly one like there, and suppose we have reduce it down to a and b. If we have an interval a and b, we sample many xk values in here, not just sampling here and there, not regularly, but fairly evenly well spread apart. Suppose you collected 500 values, and you have all these function values out of it. What is the average value out of that? That would be you add all this function value, right? And then divided by number of data we added up. Here's n numbers is divided by, and that would be the average value, right? Just like we did described in an earlier case. So I call this xk as a sample values. So what's going to happen if we collect more and more points, not all concentrated here, fairly well, you collect it distributed over a to b, you collected. What's going to happen to that value? What's that? Yeah, that center, depending on the shape of the graph, right? That meaning of the center is unclear. What, how are we going to make sense out of this average value of the central point, whatever, right? So, best thing is that you mathematically analyze this thing and pull out a Riemann sum and see what you get. The thing is that it already looks like a Riemann sum because of the notation, right? If there are many points, then their behavior is pretty much similar to regular partition rather than randomly sampling in a regular sample. Let's say n was a pretty big number. Let's think about that one. Then assume it's irregular. Assume delta xk. This xk between these is common, not changing. It's a regular partition. So delta xk is really same delta x. in the partition, before we enter function, it was about partition, interval, and all that. So what was the formula of delta x if it is regularly divided into some arbitrary n pieces? B minus a. Great. B minus a divided by n. All right? So I'm going to write this average value in sigma notation. K going from 1 through n. What's a good sigma notation inside here? That it is equal to that one. F of? No. Just writing this one into sigma notation. There's no theory or anything. It's just notation. 1 over n is out there. How do you write this one in the sigma notation, right? We're adding f of what? X. What's that? N down here? X star. There's no star. You see there's no star here, right? So we can't use a star. So what is it? K? Does that make sense? When k equals 1, f of x1. When k equals 2, f of x2. When k equals 3, f of x3. And so on. All the way up to n. So I got the number correct. So this average value is now denoted using the summation notation, right? And our goal is turning this one into Riemann sum. If it is a Riemann sum, it must have which factor? Riemann sum must have this factor. Triangle. Why did I say triangle? There's a triangle. There's delta, right? We need to have delta x in it. Otherwise, not a Riemann sum, right? Right. So we want to bring that somewhat, change that 1 over n to delta x. So can you do that? And here we can solve this n for what is n here? You see the b minus a divided by delta x, right? That's one if you solve this thing for n, correct? So since 1 over n is not varying as k going through 1 through n, we can bring that inside by linearity, right? And put it on here. Is that okay? But what's n? Right, b minus a divided by delta x. So it's k equals 1 through n f of xk. But we're not just putting it, it's a reciprocal of n, right? So what is it? Is a delta x up there, reciprocal of n, divided by b minus a, correct? Now I'm going to reorganize this one so that everything multiplied by delta x. Then it's a Riemann sum. F of xk there, right? Times 1 over b minus a. Maybe that's why I can put everything underneath it. So let's write it like this. F of xk divided by b minus a times delta x, right? So there's a delta x, and everything inside here is a function of xk. There's no xk minus 1 or xk star mixed up with the xk plane and all that. It is just xk, and b minus a is a constant. It does not change as k varies or does not depend on x, right? Does that make sense? This is a function of xk. This is delta x. Then that's a Riemann sum. So what happens to the Riemann sum when n is increasing? This approaches definite integral, right? This summation symbol changes to integral symbol from a to b, right? And all the function, except the delta x, changes in terms of x. All the xk changes x. So it's f of x. And there's no x here. B minus a. And this delta x changes to what? Dx, right? Riemann sum approaching this definite integral. Do you know what theorem this is? Nope. There's no antiderivative here. I didn't say any antiderivative here, right? Just Riemann sum approaching something. This is nearly the definition of the definite integral. And there's a theorem of integrability of what kind of function? Continuous function. If the continuous function, that's going to approach definite integral. Because this is not regular Riemann sum. This is not general Riemann sum, excuse me. This is one particular Riemann sum, right? How do you know it approaches definite integral? Because of the theorem of integrability continuous function. No matter what Riemann sum you consider, it's all going to go to the same number. So even if you choose random Riemann sum in here, they all also go to the same value in here. Right? B minus a does not depend on x there, right? For integral variable, b minus a is a constant multiple. By linearity, it goes outside and enter fairly simpler expression for inside the integrand function. This is area underneath the function, right? Divided by length of interval. Then that measures what? Average value of your sampling. Right? It's not quite intuitive, but that's what Riemann sum analysis leads us to. That if you sample 3,000 value in between that a and b, collect all the function values, and average them out, that value is probably awfully close to this value that you can calculate quickly. Make sense? Right, so here is a statement. Here's average value. If you want to calculate average value of f of x, you can get out of input value between a and b. Randomly, you keep doing that. The average value is very, very close to 1 over b minus a times the area underneath the curve. Right? That's what formula leaves, but it's curious. Try to understand geometrically what has it got to do with the average value. I don't think it's easy to understand. I think a formula is easy to remember, right? Area divided by length of interval. Okay, let's see. Let me explain that with this example. I want you to look at this problem like this. First, let's read it together. An object moves back and forth along a straight line with the velocity given by this function, t minus 1 cubed, between 0 and 3 seconds. What is the average velocity of the object? I want you to look at it like this. Suppose we have a measurement device that measures the velocity of an object every 100th second. So between 0 and 3, we're roughly measuring 300 velocities, right? At the beginning, after 100th second, you measure the velocity again. Second, next moment, you measure the velocity again. So you have data over 300 values. What is the average of these all 300 data? You add them all up, right? And divide it by 300. That's the average. If you actually do that, and that's going to be very close to the definite integral formulation that I gave you. All right, let's formulate that. Everybody remember the formula? The average velocity is equal to, right, 1 over b minus a. Here's 3 minus 0, right? And that's integral from where to where? 0 to 3. And what are we integrating? The value we're sampling, right? That's right, the t minus 1 squared dt. If you can calculate this using the integration technique, then that is actually very close to your sample added up all together, 300 samples, and divided by 300. That would be a lot of calculation, but that's almost the same as that one. It's a pretty powerful thinking if you think about it. All right, that's your exercise number 2, computing this integral. Exercise number 2. 3? Yeah. Compute the definite integral. No, compute compute the average. All right. Any question? T minus 1 squared expanded first and integrated individually. Any question? All right. Here's a little remark on integrating that one, something that we'll be doing today. Let's remark. Some of us are very clever and already figure out what to do about that kind of thing. If this is instead of 2, if it is 22, then it's going to take a long time to multiply t minus 1 to itself 22 times, right? It's almost impossible. But do you see that it's antiderivative in a slightly different way? Do you see something raised to third power? If you differentiate it, you get this one, close to that one. You see that if I do t minus 1 raised to third power, I get 3. If you differentiate that, we have 3 times t minus 1 squared. You see that? If you differentiate that, right? So I got this part matched here, so that's good, but they don't have 3. So 1/3, yeah, it's a good idea. It's multiply 1/3. And if you multiply that, then 3 cancels, right? T minus 1 squared, and it's perfect. So isn't that an antiderivative, right? I just verified that this isn't it. Its derivative is t minus 1 squared. So this looks great. It's a lot better than this guy here, right? And then what do? Just put around 0 and 3. Yeah, so it's 1/3. And here's t minus 1, third power, and 0 and 3. And that's the answer. Plug it in there. Alright? So if you actually expand this guy and compare this one, only difference is a constant. But as you subtract each other, that different constant will disappear. So you get the same number, 1. Is that right? Oh, yeah, it's 0 and 1. That's right. Okay, so how do we do this type of thing? That's chapter 6. But some of us are already doing this type of thinking. Not that because they learned this one before, but some of us already observing that there's a simple way of doing that. So I threw out there.